I would like to introduce our speaker, Dr. Brad Davis. Dr. Davis is an associate professor of civil engineering at the University of Kentucky, where he is responsible for all steel design coursework and has received excellence in teaching awards. He earned his PhD from Virginia Tech and has 8 years of experience in building design. As the owner of Davis Structural Engineering, he provides consulting services for structural vibration, steel connections, and advanced steel design applications. He has licenses in approximately a dozen states. Dr. Davis is a member of the AISC Committee on Manuals and Textbooks and a consultant for the Steel Solutions Center. He has published approximately 24 journal and conference papers on vibration and has presented a number of continuing education courses for vibrations and steel connections. Brad, thanks very much for being here today, and I'll now turn things over to you.
Well, thank you, Nate, and thank you all for attending our webinar series. This will be session 1 of 4. These 4 all stem from previous presentations that Dr. Thomas L. Murray has made, and he provided the slides for us as a good starting point for these, and we very much appreciate that. Today's session will be Moment Connections Part 1, and then, of course, Session 2 will be Moment Connections Part 2, and those will be on wind and low seismic applications. In Part 3, Professor Matt Etherton will be here to talk about moment connections for high seismic design. Finally, in Session 4, I'll be back for bracing connections. All right, Moment Connections Part 1. Our topics today will be directly welded flange moment connections, and then we have 2 flange plated moment connection types, welded and bolted. Then we will discuss column side limit states, and finally we will have a complete design example. All right, let's take a look at our connection classification curve from Part 12 of the Steel Construction Manual. This is Figure 12-1. And we focus our attention on this diagram over here on the right. This would be a piece of a moment frame. So we have a beam in the moment frame and then the columns. And if we apply load, then we will have some end moment on the beams, or on the beam. And due to the connection flexibility, we're bound to have some rotation of the end of the beam relative to the support. We can plot these on these axes over here. We have the end moment on the y-axis and the rotation on the x-axis. And we use this curve to classify connections as either simple shear connections, PR moment connections, or FR moment connections. Now, on one end of the spectrum, if we have hinged connections at the ends of the beam, we'll have no moment or 0 moment at the end. And then we'll have the simply supported beam end rotation status of S. Now on our connection classification plot, that would show up right here. That's the simple beam. At the other end of the spectrum, if we have fixed supports, then we would have 0 rotation, but we would have the fixed end moment at the end of the beam. And that's right here on the plot. If we draw a line between these, we get what's called a beam line. And of course, there's an infinite number of these depending on the magnitude of the load. One key point on the beam line is right here at 0.9 times the fixed end moment. Any connection that has a moment rotation curve that goes above this point is called an FR moment connection. This is a fully restrained moment connection. And as you can see from these, you're going to have some rotation. It's impossible to have absolutely 0 there. We will have some rotation, but it will be small. So we can treat these as fully fixed connections or continuous connections with the column for the purposes of design, just to make our design process easier. So we're dealing with these fully restrained moment connections. All right, let's talk about directly welded flange moment connections like the one shown here. Here's a diagram from Part 12 of the manual. And with these kinds of connections, which are very, very commonly used, we have the end of the beam has bevels at the flanges and weld access holes, and we have this plate that's welded onto the column in the shop. And in the field, the beam comes out, bolts to this web plate. We have the backing down here and down here, and then they make complete joint penetration welds without overhead welding. And these have the advantage of downhand welding and also this tolerance of the beam length at this flange touching the column is not super duper tight. Because we have a little larger tolerance because of the backing. Over here in this picture, you see one of these from one of the AISC connection sculptures. In this case, the beam is welding to the column web stiffeners. So this connection is coming into the column web, obviously. For this kind of connection, we can see a discussion in the manual on page 12-7. We have lots of limit states, although not as many as for some other moment connections. First, let's talk about the column flange, or girder flange to column flange weld, this one. These are typically going to be made in the field, and they're going to be complete joint penetration welds, as I mentioned a minute ago. Sometimes if you have a small piece of beam that we want to attach to the column and in the shop, and then bring this out in one piece, we may choose to use shop welds or fillet welds in the shop there, because in this case, the fillet welds can be made in the shop without overhead welding. You can turn the column various ways to not do them with overhead welding. In the field, for example, you would need overhead welding to make a fillet weld down here, so that makes it undesirable. Note, because of just this layout here, the weld access holes are going to be required to make these welds. More on these welds. First, partial joint penetration welds are not recommended for these because we will have a natural crack on the opposite side of the weld, so we don't really want to use those. If we're using the fillet weld approach, we have two options for sizing the fillet weld. First, we can size the fillet weld to develop the tensile yielding strength of the beam flange, or we can size the fillet weld to resist the required beam moment. And let's see how this can work out using the method that's shown on page 8-8 of the manual with our shortcut number 1.392. All right, so our strength of our flange in this first approach we have here is going to be less than the strength of the weld, or less than or equal to the strength of the weld. So the flange tensile yielding strength is given by this expression here for a 1-inch width of flange. So we have 0.9 for the phi factor. The yield stress of the flange, the thickness of the flange. So this is the tensile strength of the flange, tensile yielding strength. Said to equal to the weld strength, which is our magic number 1.392 kips per 16th of size and per inch of length. And this is from page 8-8 of the manual. Times 1.5 because these welds are loaded at 90 degrees. Times D, which is the number of 16ths of the weld size. D required in this case because we're going to solve for it. And 1-inch wide length of the flange, and we have a weld on both sides, so we have a 2 there. And we can back out from this the D required, or the number of 16ths required for the weld size. That's the first approach, this one right here, developing the tensile yielding strength. The second approach is to have the weld strength greater than or equal to the required strength, just computed from the required moment, divided by the distance between the flange centers, which is D minus T sub F of the beam. So from this, we can also back out the number of 16ths required for the fillet weld size. Moving to the web plate, here we need to size this plate right there. That one's going to be resisting the shear. Our design model is that the moment is resisted by the force couple in the flanges, and then the shear is resisted by this web plate. With this design, we have various limit states. We have shear transfer, which is our newly explained limit state, which is a combined bolt shear rupture bearing and tear out limit state. We also have shear rupture through these bolt holes, shear yielding, block shear, and weld shear rupture for this connection plate. Now in this case, this web plate connection is designed for direct shear with no eccentricity at all. So this is not. This looks like a single plate shear connection from Part 10 of the manual, but it's not. In Part 10 of the manual for those guys, those must resist eccentricities in the end moment of the beam. Here we have, if we have an end moment, and we will because this is a moment connection, it's going to be resisted by the flange force couple instead of this plate. Now with that, let's move on to flange plated moment connections that have welded connections between the plate and the beam. In this case, these plates are typically shop welded to the column, and that will typically allow fillet welds without needing overhead welding. And to find a picture and discussion of these, we can go to the manual, page 12-4. The top flange plate is narrower than the flange of the beam, and that's so that these welds can be made in the field without overhead welding. Similarly, the bottom flange plate is wider than the beam flange, and that also is so that the weld here and the one on the far side can be made without overhead welding. These have the advantage of having all fillet welds and no overhead welding required, and no bevels and all that kind of stuff required for any of these plates in the shop. These flange plate to column flange welds, they can be complete joint penetration welds if necessary. They can probably be fillet welds typically. Note that the plate to column flange weld, this one, must be made first before these welds over here, and that's to account for weld shrinkage. Obviously that applies down here at the bottom flange as well. We have some other limit states. Let's take a look at tension flange plate yielding. So our required flexural strength here, the M sub U, is resisted by the couple, the force couple with this force and this force down here. And those are going to be, and the moment is going to be D plus the average plate thickness apart. And the plates may be different thickness because the bottom flange plate will be wider. You may choose to make those different. Now this plate's in tension in this region right here, so we need to check tensile yielding right there. Our criterion for this limit state is R sub U can't exceed VRN. There's R sub U. And R sub U is calculated just from this required flexural strength divided by the distance between the centers of these flange plates shown down here. So that's the required strength. The nominal strength, R sub N, is from the spec section J4. This is the equation J4-1. And it's simply the yield stress of the plate times the gross area at this cross section right there. And phi is 0.9 for this limit state because it's a ductile limit state, and the strength is easily and accurately predicted. Now we also have tension flange plate rupture, and at the top flange plate anyway, I guess at both flange plates this is true. We only have welds along here typically, or I guess if we have welds along here only, then we have a shear lag effect. Our criterion again is RU can't exceed VRN, and R sub U is the same as it was in the previous slide. Now, the phi is 0.75 in this case because we have a non-ductile limit state that's more difficult to predict accurately. The nominal strength is F sub U times the effective net area, and because we have shear lag in the plate in this configuration of welds, we have the effective net area is the shear lag factor times just the net area. Well, there's no bolt holes across here, so the net area is just the gross area. Let's talk a little about the shear lag factor. I guess that's the only trick to this limit state in this case. Here we go to table D3.1. It's our big table full of shear lag factors. We go to case number 4. And you can see the configuration over here. This case applies for plates or a connected element like an angle that has these 2 longitudinal fillet welds. And they could be of different length. In our case, they're the same. L1 just equals L2, and it's just L. L is the average length in general here. For us, it's just we only have one length L. This X bar is out of plane of this picture. This would be like if you had an angle welded down to the plate. In our case, because we have a plate, X bar is just 0. So this just turns into just this piece right here. So that's our shear lag factor for checking this limit state. Let's move on to the top flange plate weld. In this case, third strength. R sub U is the required flexural strength at the end of the beam divided by the beam depth lowercase d, because that's how far the welds are apart. They're just d apart in this case. We have a couple of things that can happen as far as calculating the strength. First, if we only have the longitudinal welds, then like in this picture but without this weld, then the strength is just calculated using our shortcut 1.392 kips per 16th size per inch of length times d, the number of 16ths in the weld size, times the length of the weld, this length that way, longitudinal, and there's 2 of these, so 2 welds. So we would just calculate the strength using this simple equation right there. And the derivation for this 1.392 magic number is shown in the manual on this page if you haven't seen that before. Sometimes at the top flange, we may have welds along all 3 of these lines like this. So we have longitudinal and transverse welds in this case. And this is a special case in J2.4b and 2. And in this case, what we do is we get to use the max of 2 different strengths. And we start by calculating the strength of the longitudinal welds, and that's R sub NWL for longitudinal. And then we calculate the strength of the transverse weld, R sub NWT for transverse. And this weld is loaded at 90 degrees, so it's really 50% stronger. But for R sub NWT, we don't use that 50% increase. Now, with those calculated, we go over here, and we get to use the max of just add the 2. That's one option. Or take the transverse weld at its full 50% increase for the 90-degree angle, but then add not all of the longitudinal weld strength. So we get to take the max of these 2 in a case like this. And we may choose to have welds like that at the top flange plate. Now let's move on to beam top flange block shear. This is going to apply for beam negative moment, obviously, because if it's positive moment at the end, you don't have any tension there, so no block shear. The required strength is mu over d, and the PRN calculation we do per the spec section J4.3. Now for longitudinal welds only, the block shear pattern looks like this. Here's our tensile area, and here's our shear area. So the corners of the flange, or the corner of this plate, or the corner of the top flange is getting block sheared out, the corners of it. Now this is if we have longitudinal welds only. If we have we have a second pattern that I think we'll rarely control. It may control if you have a short plate left to right in this picture. So it technically applies, so I'll show it to you, even though, again, it probably won't control. This pattern applies whether we have longitudinal only or if we have longitudinal plus transverse welds, either one. In this case, the tensile area is all the way across the entire top flange, like this. So in the elevation view, you see the tensile area there. The shear area is all across the web like that. And this technically applies, probably not going to control, but hey, there it is. Next, let's move to the compression flange plate. In this case, we have this plate is in compression, so we've got to think about local buckling. we're going to show that these plates are non-slender per table B4.1a, which is for axial compression. At the bottom flange anyway, we have two different cases. We have this unstiffened element outside the weld there, and then a stiffened element in between. For the unstiffened element, we're going to use case 1 in table B4.1a, and that's right here. This is the same case that you would use for, say, a W-shaped column flange. For the stiffened element, we use case 7 that you see right here. Now, looking at these in the table, you'll see them like this. There's case 1, and there's case 7. You can see case 7 looks just like our case. All right, we don't only have local buckling, we also have the potential for flexural buckling. So let's take a look at this. In this case, we have a little piece of, this is like a little column turned on its side right here. And sometimes this distance is not small like this. Just to make the thing fit together right, sometimes this dimension can be quite a bit larger than this. There's lots of things that can happen. The required strength is going to be mu over the distance between the centers of the flange plates, so it's D plus T average. The strength we calculate using the spec, section J4.4. It's going to depend on the L sub C over R ratio, what we used to call the KL over R ratio. If that's less than or equal to 25, we get to just use the yielding strength of this cross section right there. If this is exceeding 25, then we have to calculate the flexural buckling strength of this little bitty column there. And we use chapter E for that, section E3. For both of these, phi is 0.9, the unbraced length is KL, and that's going to be 0.65 times this L because it's like a fixed case, like fixed there and fixed there. The radius of gyration of the plate about its minor axis is the thickness of the plate divided by square root of 12, as it always is, for a rectangle. Now let's talk about the bottom flange plate welds. In this case, we're only going to have longitudinal because we want to avoid the overhead welds. So looking down at a plan, a section looking down, you see the web hatch there. We're cutting a section through the web. You see the plate below, the flange above, and the plate's wider, so the welds are along here and here. If we tried to weld the C-shape, it'd be an overhead weld hidden under there, so we don't want to do that. The required strength is mu over D, and the strength is just simply from our shortcut equation. 1.392 kips per 16th size per inch long times the number of 16ths times the length times 2, because there's 2 of them. Moving on to the web plate connection. Here, it's exactly the same as what we discussed before for the directly welded flange connections. If there's any end moment at this beam, it's taken out by the flange connection, so we designed this plate for straight shear with no eccentricities considered at all. With that, let's move on to flanges, to a second type of flange plated connection. This time bolted. In this case, we have the flange plates are bolted to the beam flanges like this. And as you see in this picture over here, which is from one of the steel sculptures, the beam is connecting into the web of the column, and the column web stiffeners are cut so that they can serve as these flange plates. And then, of course, these are bolted up in the field at the web and the flange. We can see a picture of these in the manual, page 12-4, along with some discussion. These flange plates are usually welded in the shop, which provides the advantage of being able to use fillet welds a lot of times without any overhead welding. Like, for example, again, if you tried to fillet weld this in the field, you'd have overhead weld there and up here as well, so that wouldn't be good, but these can be welded in the shop typically. Now, for tolerance sake, we need to be able to push this top flange plate up a little bit. They're usually 3/8 above the tabulated beam depth, and that's to account for tolerances in the beam depth, and also because of the out of square tolerances that you see in this picture, which is from the manual table 1-22. All right, so we have the flanges are going to be placed a little high like that. Moving on to the flange plate to column flange welds. We could use complete joint penetration welds. Probably not going to need to do that. Typically, we're hopefully going to have Phillip welds there. And if we do end up welding this in the field, then the welding must be done before the flange bolting. Let's look at the tension flange plate limit states. We have several. We have 4 here actually. First, the required strength is MU divided by the moment arm for this flange force couple. That's going to be the depth of the beam plus the thickness of the plate, assuming both of the plates are the same thickness. We have tensile yielding along 1, tensile rupture along 2. We have block shear, a couple patterns of that, and shear transfer at the bolts. Let's take these one at a time. First, tensile yielding would be on the gross section, like section 1 there. The strength for this, the design strength, would be phi times Fy times Ag, as it always is, and phi is 0.9. Moving on to tensile rupture, that's through the bolt holes. Here we have the same equation we've seen before. The trick here, I guess, is what's A sub B. In this case, A sub B is A net through this section. It's a section across there with the effective hole diameters subtracted. And phi is 0.75. We don't have any shear lag here, so we don't have the U factor. Flange plate block shear, well, lots of stuff going on here. We use equation J4-5 for this. If we have 2 rows of bolts like shown here, we have 2 patterns. We have the corners of the flange plate block shearing out, that's one, or we can have this piece in the middle block shearing out. And typically you can tell pretty easily by looking at those which one controls, because it only depends on comparing the sum of this distance plus that distance to this distance. The one that's smaller will be the one that controls. If we were to have a very large beam with a wide flange and multiple rows of bolts, we can have something like this. We can have the corners block shearing out like so. That's one. We can have this whole middle part block shearing out. There's another one. And we could have this. I'm thinking it probably wouldn't control, but it's possible. So we always have to account for all the different ones, all the different patterns. Either calculate all of them, or be able to tell by looking at them which ones won't control. Now, shear transfer. This is again a newly described or explained limit state in the spec in manual. The idea here is that at each bolt, we want to calculate the effective fastener strength. And the effective fastener strength at one of these bolts is the minimum of the bolt shear rupture strength or the bearing and tear out strength of both connected parts. So actually we have five numbers to calculate at each bolt. Determine that at each bolt, sum those up, and that's the nominal strength of this connection for the shear transfer limit state that we compare phi Rn to R sub U. Moving to the compression plate limit states, we have a couple here. We have shear transfer of the bolts and local and flexural buckling. Shear transfer between the plate and flange. This is the same method as for the detention plate. Same deal here. The only difference could be the tear out L sub C's could be different, so we may have a little different number here than we had at the tension plate. We also have local and flexural buckling because this plate is in compression. This is very similar to the flange plate welded connection discussion we had earlier, where we have local buckling of an unstiffened element here and over here, or the stiffened element in between these bolt holes. And we check it exactly the same way as I showed previously. Now we also have flexural buckling of this little column section in here, checked exactly the same way as we did previously today. With this kind of connection, we also have a couple of different new limit states. Well, we have a couple of these related to the beam. Let me just jump right into the first one, reduced flexural strength. In this case, we go to section F13.1, and the idea here, in this case, say we have negative moment, we have stress risers at these bolt holes, so we can have flexural rupture in this region. And this will almost always have a strength that's quite a bit lower than phi-EMP. So sometimes as a connection designer, you'll see the engineer of record calling out to design the moment connections for the capacity of the beam, and you know immediately you're done for this limit state because you can't use holes in here because you'll never develop phi-EMP of the beam. So if we have the actual end of moment, we can go with this kind of connection. Now, we need to determine whether or not flexural rupture is realistic, and we do that by comparing the rupture strength of the flange in tension to the yielding strength. And if it's lower than the yielding strength, then this could happen, and we would go ahead and calculate the strength for flexural rupture with this equation. And you can see what we're doing here. We're taking F sub U times Sx, and this is the gross section modulus, elastic section modulus, and ratioing it by the net area of the flange, of the tension flange, to the gross area of the tension flange. And this is the spec committee being really nice to us and not making us calculate the net S for this. If the rupture strength is higher than the yielding strength, then this doesn't apply, so we don't have to do anything here. Y sub t is just a factor that accounts for the ratio of Fy to Fu, and note it's going to be 1 for our preferred material spec 8992. Beam flange block shear. Several things going on here. Say we have 2 rows of bolts, like this typical case. Well, block shear with the corners of the flanges being block sheared out. If we have multiple rows, we could have this again, like we had on the plate. The corners of the flanges are being block sheared out, or technically you could have this pattern where these areas are block shearing out. Although it seems pretty unlikely that would control, but hey, who knows? There's all kinds of proportions of these connections. Next, we have what I call a Flange Web Pattern. It's similar to the pattern I showed earlier, although it's much more realistic in this case. I've been told this actually occurred in a lab test. So this is a realistic pattern where we have tension through the flange and a shear through the web. So we have the tensile areas along this line shown here, and there's the shear area that way. I think we do want to check this one. I've seen it control in examples that I've generated. Moving on to the web plate and web bolts, same deal as before. We're just designed this web plate with no eccentricity, straight shear. Now let's move on to a discussion of the column side limit states at moment connections. It's a big topic, and it's a very big deal. So let's spend some time here. For these, our go-to references are the specification section J10 and the design guide 13. Those are our go-to references. We have these 6 topics. First, we have the flange local buckling limit, or flange local bending limit state in section J10.1, flange local yielding, or web local yielding, web local crippling, web compression buckling. We need to talk about transverse stiffener design, and finally, web panel zone shear. Let's take these one at a time. First, flange local bending. The deal here is that oftentimes our force is being delivered by a plate or a flange that's transverse, as shown. In this case, it's transverse to the column, and this plate is stiff in plane. It's delivering the force to the column flange, which is being bent out of plane. So if this column flange is not very thick, it's relatively flexible compared to this plate in plane, and you could have a stress distribution like this, which is a figure from Design Guide 13. So we could have a hot spot here in the weld, and that's not good, so we want to prevent that. We prevent that, and by the way, this only applies to tensile forces. We prevent this problem by satisfying this inequality, whereas phi is 0.9, and here's our equation from section J10.1. You can see it's just a function of the column flange yield stress and the column flange thickness. If T sub u exceeds the design strength, then we need a half-depth web stiffener in this region right here to hold that flange back, to keep it from bending. Moving on to web local yielding, we go to section J10.2 for this. And here's the idea here. This applies for either tensile or compressive forces coming in. And we have this bearing length that will be the thickness of the plate or flange, plus the fillet weld size on both sides if you have fillet welds. Now this force coming in is going to cause a horizontal stress field over here, either tension or compression, depending on the sign of this. And our design model is that the critical section is at K over from the face of the column, and that the load spreads at 2.5 to 1. And you can see if we're not near the top of the column, it can spread both directions. This results in this simple equation for the strength down here, phi times the yield stress of the column web and the web thickness for the column, times this length of the critical section that you get from just this slope. Phi is 1 for this limit state. If the required strength exceeds the design strength, then we need half-depth stiffeners or doubler plates in this region right here. Web local crippling is a slightly different type of limit state. It only applies for compressive loads, and it's basically buckling of the web in this region. And our bearing length here is going to be the thickness of the plate or the beam that's delivering the load, plus a weld on both sides if you have those. If C sub u exceeds phi rn, then you need 3/4 depth web stiffeners or doubler plates in this region. Our equation from J10.3, let's look at the one for load away from the top of the column. Phi is 0.75, and our equation is this. You see our bearing length in there, and these are just column dimensions going in. Q sub F is a factor that only applies for HSSs. It does not apply for wide flange shapes, so it's just 1 for us here today. Web compression buckling in section J10.5 with this limit state. It only applies when you have opposing compressive forces like this. They don't have to be equal, but they need to both be in compression and opposing. So they're going to cause buckling in this region of the web. Our criterion is C sub u can't exceed phi rn, and here's our equation from section J10.5. These are the column dimensions going in there, and the column web yield stress. I guess H is the only non-obvious thing here. The H is a clear distance between the fillets in the column, and the fastest way to get that is using the H over TW ratio in table 1-1 of the manual. If the required strength exceeds the design strength, then we need full depth stiffeners or doubler plates. All right, now the discussions on the last few slides were for connections that are not near the top of the column. If the load is being delivered near the top of the column, like shown in the picture on this slide, then the strengths are different. They're about a half of what I've shown before. And some of the equations are not just exactly a half, but roughly a half, and exactly half in some cases. So look in these sections for the details for those calculations. Now, if we need transverse stiffeners, then we're going to have to add them, and we need to be able to design them. So let's see how we can do that. Our go-to section in the spec is section J10.8, near the back of section J10. We're going to be coming up with the width of the stiffener and thickness of the stiffener, and it's going to be a function of the loads and the plate or flange that's delivering the force to the flange. We have some proportioning guidelines for the stiffeners, and these are very useful for coming up with our trial section of stiffeners. Those are fast and easy, and they'll control quite a lot. The first requirement is that the width of a stiffener plus half the web has to be at least 1/3 of the width of the flange or plate that's delivering the force. So that's number one. Second, the thickness of the stiffener has to be at least half of the thickness of the flange or of the beam flange or plate that's delivering the force. Third, if the stiffener is in compression, we need to satisfy this inequality for local buckling, and it's that the B over T ratio for the stiffener shouldn't exceed this 0.56 square E over Fy, and the Fy is of the stiffener. And this is just case 1 from table B 4.1a. Finally, one more. Also for local buckling, the thickness of the stiffener has to be at least the width of the stiffener divided by 16. And that's what you'll get if you put 36 in here. Now, if we need stiffeners in here because we've exceeded some limit state in the previous slides, we're going to need to know how much force goes in the stiffener. So we probably couldn't calculate how much force actually goes in there at the ultimate strength. Even if we tried, we could calculate something, but I don't know if it probably wouldn't be exactly correct. So we need a force distribution design model. We have design models all over the place in structural engineering, so we need one here. To get this, we go to section J10.8 and more help in Design Guide 13. Design Guide 13 is a little dated, but the principles in there are still valid now. So this is a design model that's fully described in here. Here's our model. The column resists up to the design strength for each of the limit states. Any excess load must go to the stiffeners. And this is a very simple design model. And if we had strain gauges on there and we measured the force, maybe we wouldn't get this, but this is our design model. And this is what's been used for a long time, and it's a good model, so that's what we're going to do here. And it's what's in the spec too, by the way. Here's the idea. I guess just in equation form, you have the stiffener force is TU net or CU net. And that's going to be the force coming into the flange minus the weakest of the design strengths that are applicable at that flange. So it could be written like this as well. First thing we need to do is make sure we have enough area to resist the force. And what we're going to do is look at yielding on this, what we call AST, which is the contact area of the stiffener at the flange. So this line plus this line. We're going to have clips here to clear the fillets or fillet welds for built-up. So that's going to reduce the area down from B sub ST, or B sub S. Our criterion looks like this. We have our required strength, can't exceed our design strength, and our design strength is just the yielding strength. So Fy times AST required, we already know these, so we back out the area of the stiffeners that are required. So we back out what we need. What about the weld from the stiffener to the flange? For this, it's recommended that this weld develops the stiffener contact area. This dimension, this area right here, develops that area in tensile yielding at the column flange. For fillet welds, we can derive a required size using this equation then, where we have the strength of the stiffener in tensile yielding equal to the weld strength. So the stiffener strength in tensile yielding is phi 0.9 times Fy times that flat width contact area times the thickness of the stiffener, set the equal to our weld strength. We have two welds. We have a weld on both sides of the stiffener. We want that to keep the stiffener from warping or bending from the shrinkage. Come back out the D required then, and this is the number of 16ths that's required. So we have 0.216 times the yield stress of the stiffener times the thickness of the stiffener. Note, if necessary, we can resort to a complete joint penetration weld there also. All right, we also need to size the stiffener to web weld along these two lines. And for this, what we do, per section J10.8, is we have the required force going into the stiffener, the net on both sides, and we could have a tension on both sides or compression on both sides, or it can be compression and tension like shown here. And we're just going to use the algebraic sum. In this case, this load's pushing to the right, and so is this one, so they add. So the shear, the web is the two added. If one of these was flipped around, you could have a subtraction in there. So you just got to look at it and just determine what the web shear would be. Another thing, when we have full depth stiffeners required, we need to treat this little region in here like a little horizontal column that's being compressed by these forces right here. Now, the way we do this, we go to section J10.8. It tells us to design this as a cruciform shape, where we have the stiffeners and then some region of the column web that's effective with the stiffeners to make a little column shape. If this load is not near the end of the member, then this height is 25 times TW. If it was at the top of the member, then it would be 12 times TW. Going from there, our criterion is the max CU. These can be different. The max of the two can't exceed VRN, and VRN is in compression per the spec J4.4 that we've seen before a couple of times. In this case, the A and the R are for the cruciform shape. The R is the radius of gyration about the vertical axis in this picture. And the length, the unbraced length, KL, per section J10.8 is 0.75 times H, and H is the depth of the column clear of the fillets. And then from the unbraced length divided by R, we get the design strength to compare with C sub U. All right, let's move on to web panels on shear. And this is in section J10.6 of the specification. In steel design, we don't usually spend a lot of time thinking about shear for beam design or column design, because if, for example, for a beam, if it's okay for flexure and okay for deflection and forward vibration, say, then it's going to be okay for shear, oftentimes by multiples. There's just a few counterexamples of that, and this is the big one right here. In this case, the shear is a very, very big deal. And the reason is because you have this moment, and you could have this moment over here. They're being resolved into their force couples at the flanges. Those are obviously going in opposite directions, so you have these zones in here that have very high shear force. So let's take a look at one of these. Let's say we looked at section AA in this case. Our criterion for the web would be that the R sub U can't exceed VRN, and R sub U would be the force pushing to the right here in this picture. Now let's see what that would be. That would be first, take this MU1 divided by the moment arm, DM1, and add to that the same on the left side, the MU2 over DM2. And in this case, the story shear above is going the other way, so minus VU from the column. Now, if we had directly welded flanges, say, like this picture looks like, DM1 would be from the centers of the flanges. So it would be D1, depth of the beam on this side over here, 1, minus the flange thickness. It's similar on the left side. And these forces can be pretty enormous, as we'll see in our example problem later. So these panel zones can get totally hammered by these shears. As far as the strength goes, typically we're using section J10.6A, which applies when the effective panel zone deformation on the frame stability is not explicitly considered in the analysis, in the structural analysis. Typically we're going this route, so here's our set of equations. First, if we have our column required strength above, which in this section is called alpha times P sub R, for us that's just P sub U in the column for LRFD. So if our column force does not exceed 0.4 times the yield force in the column, just Fy of the column times the gross area of the column. If that's true, then the axial load is relatively small. It's not going to have a great effect on the shear strength of the column, so the panel zone shear strength is just the plastic shear strength. 0.6 times Fy, that's the shear yield stress, times the depth of the column, times the web thickness of the column. Now, if we do have a higher axial load, exceeding 40% of the piece of Y, then we have the same thing, plastic shear, but a reduction factor tacked onto the end. And again, this alpha P sub R is just P sub U for us because we're using LRFD today. Alpha is something else for ASD, 1.6. Now, we could use section J10.6b when the effective panel zone deformation on frame stability is being considered. So you could use that if you wanted to, but we're going to use J10.6a today. And I think that's probably the typical thing that's done. All right, say we back up a little. If we have, well, actually I say it here, if R sub U exceeds phi Rn, then we need it, and this is our phi Rn for the column web. If that's true, then we need a doubler plate, or plates, one on both sides perhaps. And so we would want to slap a plate up against the web of the column and weld it, mainly welding it on the sides with minimal weld at the top and the bottom. And these are expensive and undesirable, so we like to avoid them if we can. We need a design model for the shear that gets in the doubler plate, and we use the same approach that we used before on stiffeners for the stiffener to flange connection. In other words, we take the strength of the column web, phi Rn of the column, and this is the calculation from the previous slides that I just showed you. Any excess load above that has to go to the doubler plate. So this net force has to go to the doubler plate. Note, if we need very thick doubler plates, or if we calculate a required thickness that exceeds an inch, we're going to go to two doubler plates, one on each side of the web. As far as the doubler plate strength goes, for this we go to section J10.9. It just tells us to calculate the strength per chapter G. Now, going to chapter G, the most applicable looking provisions in there would be G2.1b. So we're going to use that. And here we go. The evaluation criterion would be the VU in the doubler plate can't exceed phi VN for the doubler plate. And phi is always 0.9 in subsection B. Here's our equation for the strength, the nominal strength. We got the plastic shear strength times our reduction factor for buckling plus post-buckling strength, CV1. And what we're going to have here is if HP over TP does not exceed this limit, this yielding limit, the CV1 is just 1. And that means you have a 1 going in here, so the strength ends up being just the plastic shear of the doubler plate. So yielding controls the behavior, we would say. If you have a skinny enough doubler plate, slender enough, then you would need to use this reduction factor. I'm thinking that's probably pretty unusual. By the way, you need a KV to go in here, and I would just use the lowest KV in that section, which would be 5.34. Although you may argue for some other values instead. Okay, with that, let's move on to a design example. And this will finish off the whole rest of the webinar today, the webinar session today. In this case, we have a directly welded flange moment connection, and you see we have W24 by 103 beams on both sides, and we have 882 kip foot moment at both of these, so we have pretty high moments. We have a maximum shear of 75 kips in these two beams. They are connected to a column, W14 by 159, 8992. Column axial loads are 1,200 kips above, 1,335 kips below, and the column shear at this level is 90 kips. It's going in the direction shown. You can see that we have these directly welded flange connections with the complete joint penetration welds with backing below. We're going to try to use 3/4 inch diameter grade A325 bolts in the web and 70 KSI welds. All right, we go to table 1-1 and pull some properties and just dimensions for our W23 by 103, W24 by 103, and our W14 by 159. So we just pull these out of the table. First, let's address the W24 flange to the column flange weld. In this case, we have some pretty good size moments, and so it seems futile to even think about Phillip welds. Also, if we went to Phillip welds, these are made in the field, so we would have overhead welding there. So forget that. So from all that, we have complete joint penetration welds with the backing bars, as shown in the diagram. What about the W24 web to column connection? Here we have a single plate on both of those, and we're considering no eccentricity at all, as we mentioned a couple of times already today. All right, so let's look at that web connection for a second. In this case, this is what I want to try. I want to try a plate 5/16 by 3.5 wide by 14.5 inches tall, A36 with 5 3/4 inch diameter grade A325N bolts. And we have standard holes. 3-inch bolt spacing, 1.25 inch edge distance here, 1.5 inch edge distance there. Our required strength is 75 kips, and because the shear connection part of this problem is not really the emphasis of today's session, I'm just going to give the strength of these guys. We have shear yielding, shear rupture, block shear, shear transfer, and weld rupture. And again, these are from straight shear, no eccentricity at all. We get these strengths. The closest to the required strength is this one, 81.5. These are all okay. So our web connection is good to go. We know that this connection has 5 bolts. That's exceeding the length of the connection is exceeding the T/2, a capital T/2. So everything is all good. So we're going to use this connection at the web. Moving on to the flanges, which are the star of the show in this problem, obviously. We need to get to decompose these or represent these moments by force couples at the flanges. So we have 882 kip feet, and the magnitude of the force in this flange, and same over here too, is going to be that moment divided by the moment arm. The moment arm will be the distance between the flange centers. So that's going to be the depth of the beam minus the beam flange thickness. So from that we get 450 kips, and that's at the tensile or compressive forces at all of them. So you see we have a pretty good size force, 450 kips coming in at each of these four connection points at these CJP welds. So to summarize, this is what we have. We have these couples have 23.5 inch moment arm and 450 kips in tension there, compression there. I call these 1, 2, 3, and 4. So at 1 we have 450 in tension. Here we have 450 kips in compression, tension there, compression there. So this is what our column, flange, and web must resist. Good luck, right? 450 kips. So let's go calculate some strengths. First, let's start with column flange local bending. And that only applies at tensile locations. So here at 1 and down here at 3. Going to our equation from section J10.1, plugging in the column flange thickness. We have phi of 0.9. Plugging these numbers in, we get 398 kips. Pretty strong, but not strong enough. So for this loading, we know that half-depth stiffeners are required at 1 and at 3. We know that at this point. All right, let's check out the others and see what happens. Let's go to column web local yielding. And this applies at all of the locations because this applies for tension or compression. Our bearing length will be the thickness of the beam flange, and that's 0.980 inches. We don't have any extra bearing length because of the welds above and below. Because we have CJP welds, we don't have Phillip welds extending above and below the flange. These plates are not near the top of the column, so we have a 5 here. So run through the numbers, we have 370 kips. Again, pretty strong, not strong enough. So what this tells us is we need half-depth stiffeners everywhere, at all 4 locations. So bottom line is we need full-depth stiffeners top and bottom, between 1 and 2 and between 3 and 4. Moving on to column web local crippling from section J10.3. Here again we have the same bearing length from before, the beam flange thickness. Plug in the numbers in this big equation and mercifully spare us showing the numbers plugged in there. We get 556 kips. Now that actually is stronger than the applied force. Note this only applies to the compression forces or compressive forces. So this one's actually okay. Because this web's pretty stocky, so buckling is not so much of an issue for the column web. This is a buckling type of failure mode. All right, moving from there, we know we need transverse stiffeners, so we need to come up with the required force. So let's look at the one at the top. At TU1 up here, our net force for the stiffener will be the required force coming in, 450 right here, minus the minimum strength from the 2 different limit states that apply at this tensile force. At tensile forces, flange local bending applies, so we have 398 there, and web local yielding applies, 370 there. So we assume that the column takes up to the 370, but then the stiffener has to take everything after that. So the stiffener ends up taking 80 kips. This pair of stiffeners takes 80 kips. At CU on this side, it's the same deal. We have the required strength, 450, minus the weakest of the applicable limit states. In this case, the web local yielding is the only one that fails. So we only have the web local yielding strength in there, 370. Again, we end up with 80 kips there. So here's our stiffener. It's got 80 kips pulling to the left, 80 kips pushing from the right in compression. At the connection to the web, it has to resist the algebraic sum of those, or 160 kips. Let's calculate let's try to come up with the size of stiffener that we need. So we need to make sure that we don't have yielding on this little piece right here, this contact area, and of course this buddy up here. So let's take this required force 80 kips and set that equal to the tensile yielding strength of this little contact area, 0.9 for phi times 36 KSI times the A of the stiffener that's required. Back out the stiffener, the required area of the stiffener, 2.46 square inches. So let's try a 1/2 inch by 6 inch plate, 2 of them. Let's see what clip we need for this W14 by 159. We have to clear the fillet in there, obviously. So here's how we do this. We go for the K detailing, which is the fractional detailing dimension, and subtract off the flange thickness, and we get 1.31 inches required for the clip. So we're going to say we're going to use a 1.5 inch clip. So this will be 1.5 inches clipped across here, and we're going to have a 45-degree angle, so it's 1.5 clip this way also. So this area of the stiffener would be 2. This is only half of it here, so there's 2 there, 1 on both sides. 6 minus 1.5 inch times a 1/2 inch thick, 4.5 square inches for that contact area. That exceeds the required, so we're in good shape. So okay, so let's try this plate 1/2 inch by 6. Let's check our proportioning guidelines for the stiffeners. We have our thickness of our stiffeners 1/2 inch. It's at least as big as the beam flange thickness for the beam flange that's delivering the force, 0.49 inches. So it's okay. The minimum width, the width of the stiffener plus half the web thickness has to be at least the width of the beam flange divided by 3. The beam flange is what's delivering the force to the column flange in this case. So plugging our numbers in, we see that this is 6.37 inches. That exceeds just 3 inches, so it's okay. This proportioning limit doesn't come into play very often. Doesn't usually amount to anything. Usually it's kind of like this. Moving on to local buckling, because we have compression coming in to 4 of these locations. We have the B of the stiffener divided by the thickness of the stiffener. That's 12. We compare that to the limit from table B4.1a. This is case number 1. Plug the numbers in. This is 15.9. Since 12 is less than that, so that means this is a non-slender element, so it can't have local buckling. It could reach 36 KSI without local buckling. That's what this means. So at this point, we can say use plate 1/2 inch by 6, A36 top and bottom. So we have 2 of them, obviously, near side and far side of the column. All right, let's go on to the stiffener to column flange fillet welds. Let's try fillet welds anyway. And so we want to try to see if we can develop the plate yield strength there. We derived this expression before. We can see that we need this many 1/16ths of weld size to develop the stiffener plate. So plugging in the stiffener thickness, stiffener yield stress, 3.89 1/16ths is required. These are always going to be double-sided welds. The minimum from section J2 of the spec is 1/4. So we can say we're going to use 1/4 inch double-sided fillet welds at the stiffener to flange connection. Moving on to the stiffener to column web welds. Here, the total force at the web. I guess we should do it this way. The net force being delivered at this tensile force over here is 80 kips total. We're only showing 1 stiffener, so it's 40 kips there. Same deal over here. We have 40 kips there. So that means the weld along here needs to resist the sum of these two, or 80 kips. And we need to determine what's the length of weld that we have that's available. And for that, let's take a look at this expression right here. The length of weld that we have will be the depth of the column minus 2 times the flange thickness of the column, and minus 2 clips, 1 there and 1 there. And that is 15 inches minus 2 times 1.19 minus 2 times 1.5 inches, or 9.62 inches. Now with that, first thing we need to do is see, well, will that fit in here? And for that, let's look at this T dimension over here. The capital T dimension is 10, so the flat dimension of the web is large enough to have this. So we're going to say use 9.5 inches worth of weld. So solving from the required strength equal to the design strength, we get that we need 3.02 1/16ths inch of weld on both sides. The minimum is 1/4, so we're going to say use 1/4 inch double-sided fillet welds along the stiffener to web connection. We should always check base metal strength when we're checking fillet welds. We can tell a lot of times it's not going to control, but let's go ahead and show one of these checks here just to demonstrate. In this case, let's check the base metal strength of the column web. So it needs to resist 80 kips from this stiffener plus 80 from the other one that's not shown. So it's 160 kips total. Now, the strength here will be from section J2 of the spec, points us to section J4 for the base metal strength. And this check has traditionally been done using the shear rupture strength. So the shear rupture strength of the column web would be phi times 0.6 f sub u of the column times the column web thickness times the length of this weld, and then times 2 because there's a shear plane above and below the stiffener. So plugging all these numbers in, we get 414 kips. It greatly exceeds the 160 kips, so it's okay. Now, so far, this is what we have. We have our joint here, and you see we have the 2 plates We have a plate near side and far side, 1/2 inch thick by 6. We have 1/4 inch welds at the web. We have 1/4 inch welds at the flanges, also double-sided. Now let's dig into the panel zone shear strength and see the carnage here, because it's going to get ugly with forces this size. And this column's only sort of moderately large, so we're not expecting good things to happen here. So let's go ahead and dig in. You see we have 450 pulling this way, 450 pushing this way, and 900 going the other way down here. So that's the shear on this, less this 90 kips there. So let's go and see here. The VU then is 450 plus 450 minus 90, or 810 kips. You can see that better in this slide. You got 450 plus 450 pushing this way, and 90 going the other way, so you got 810 kips of shear in this region. Nothing to sneeze at, obviously. Now, let's calculate the strength. The column axial load is alpha times P sub r. That's just our PU in our case because we're using LRFD. I'm going to use the average of these two, or 1270 kips. 0.4 times PY of the column is 934 kips. Our column load is higher than that, so we're going to have our reduction. So let's see how that goes. Here we said our alpha P sub r here exceeds 0.4 PY, so we do have our reduction, and so we have this equation with this reduction right here in it. So we plug all the numbers in, and we get 259 kips, pretty strong, but nothing compared to our load. At this point, the column can resist up to this, and the doubler plates are going to have to resist everything above that all the way to the 810 kips. All right, let's see what we need. I'm going to assume yielding controls, not buckling, because we're going to need a pretty thick plate, and I don't think buckling is going to be an issue. Since we have such a large force, let's try grade 50 plates. Here's our strength for the yielding controlling at 0.9 times 0.6 times 50. Depth of the column. This is what's done in Design Guide 13, so I'm reproducing that here. Thickness of the plate that's required, set to equal to the force that the doubler plate's got to resist. It's the 810 minus the 259. So this is what the column can take. This is what the total panel zone has to resist. So the doubler plate's got to resist the net. So we need 1.36 inches worth of doubler plate. So I want to try 2 3/4 inch doubler plates because I don't want an inch and a half or an inch and 3/8 plate. We need to verify our assumption that we don't have buckling. So we have HP over TP. That's 12.6 over 3/4 of an inch, 16.8. It's way lower than our yielding limit. Again, this is I conservatively calculated this using the K of 5.34, which is the smallest value in that section of Chapter G. Shear yielding controls is assumed. We know that the plates we are trying here are okay. So we're going to say use 2 3/4 inch thickness grade 50 doubler plates, one on each side of the web. Are the welds first? Let's look at the long side, the vertical welds. And I'm going to use the approach that's in Design Guide 13 that was used for equation 4.4-7. And the idea here is to try the fillet weld, see what fillet welds we need to develop the required doubler plate thickness. Now, the required thickness was at 1.36 inches that we just calculated. And we're going to try to fillet weld like this. We're going to bevel the doubler plate, and then we're going to fillet weld along there. We're going to try that and see if that will be reasonable. And you can see the source of this figure there. So here's our strength for our doubler plate in shear. We got phi at 0.9 for doubler plate shear for the panel zone. 0.6 times Fy, we have 50 KSI plates. We have the thickness of the plate that's required to resist the doubler plate required strength. We have 1.36 inches, but we have 2 of these. We have one on each side of the web. Set to equal to the weld strength on a per inch basis. and we see that we need 13/16 worth of weld. That's pretty large, so we're going to use what's called a doubler plate weld in AWSD 1.1. It looks sort of like a CJP weld in here, but it's not a CJP weld. Go in there to clause 4.3, and you can read more about that. Bottom line is that weld develops the doubler plate. So the doubler plate's good. This weld develops it, so the weld's good. So we can move on from there. Now, as far as the short side, the horizontal welds at the top and bottom of the doubler plate, we're attributing very little force to those. We're treating these doubler plates as if the load is mostly coming in from the sides. So we need minimal welds here. So what we're going to do is have the doubler plate coming in. This is a section view looking at where you see the stiffeners and the web, and then the doubler plates coming in like this. We basically have the stiffener to web weld there and there, and here and here. And I'll just sort of leave it at that, in that we're not attributing much force from the doubler plate into these welds. Now, there's a lot of information on doubler plate welding out there. I'll point you to DG13. Has lots of cool figures in there and explanations. Also, in the AISC 341 2016 edition, in the commentary section E3.3, and in the Welding Design Guide DG21 section 4.3.3. Now, the final design then you see with the doubler plate in there, 3/4 inch doubler plate near side and far side. And we're calling out like this. We're not calling out a CJP weld. We're calling out a doubler plate weld per this AWS clause. And I think that's it. All right, with that, that's the end of session number 1. Thank you all very much for attending. Next up is next Wednesday, we have moment connections part 2. And in there, we have 2 kinds of moment connections that each have prying action associated with them. We have T-stub moment connections and then end plate moment connections. And with that, I'm finished with this, so back to you, Nate.
All right. Thanks a lot, Brad. So now we're going to move into our question and answer portion of the webinar. And for that, I do want to direct everyone's focus now to the slides window. So you can minimize the media window and look at the slides window. We're going to start out with some polling questions for the audience to test their understanding. And there in that slides window, you can see the first polling question. It's a true-false statement, and it is as follows. For the moment connection discussed in this session, the web connections must be designed to resist moment. Is that statement true or false? And all the audience members can take a moment to select the answer that they think is correct. Again, that true-false statement is, for the moment connections discussed in this session, the web connections must be designed to resist moment. All right, so I'm going to go ahead and close this poll, and we'll see what the audience thinks is the right answer. All right, Brad. So looking at the results that came across here, it looks like 87% of the audience think that that answer is false. Did they get that answer correct?
That is correct. And the idea here is that inevitably there will be some end moment in any connection, but it's going to be it's obviously going to be resisted by the flange force couples in this case. This is completely different from, say you had a single plate shear connection in part 10 of the manual. there are no flange connections, but yet we know we do have some in the moment, and that web plate's all there is. So in that case, it must resist the eccentricities. But here, no, the flange connections are going to resist any eccentricities, any beam end moment. So we don't have any going into the web plate.
All right. Good job, everyone. So let's try one more. See if that one's any more difficult. This is also a true-false statement. And that statement is as follows. Column web compression buckling is checked when there is a moment connection on only one side of the column. Is that true or false? All right. Staying on that polling question, take a moment to answer what you think is correct. Column web compression buckling is checked when there is a moment connection on only one side of the column. All right, so we're going to go ahead and close this poll. Let's see what the audience thought here. So Brad, on this question, it looks like 84% of the audience think that that is false. What was the answer we were looking for here?
Well, that's correct. It is false. The spec just says for the column compression web buckling that you only have to check that if you have opposing compressive forces coming into that elevation of the flange. So you don't have to check that if you only have a beam on one side just delivering the force. And also, like in our example, we did have a beam on both sides, but in that load combination, you do not have to check web compression buckling there either, because we have a tensile force coming into one flange, and right across from it, we had a compressive force coming into the other. So in that case, you would not have to check it either. You got to have opposing compressive forces, like say you have like a gravity load combination, like a 1.2 dead plus 1.6 live. There, you're going to have negative moments at the ends of each of the beams framing into the column. So the bottom flange of each beam would be delivering a compressive force to the column. So then you would have to check it there.
All right. Thanks, Brad, for those explanations. So let's go ahead and move into some questions that we received from the audience over the course of your presentation. So if the audience can continue to look in that slides window, the first question brings us to slide 13. And the question is as follows. Can you elaborate why PJP is not preferred in directly welded flange connections?
Okay. Well, imagine you have a beveled flange, like we've shown in so many of these pictures, and you don't have the backing underneath. And then you come in from above and you weld. You put the weld down for the partial joint penetration and fill in that bevel. You won't have a perfect weld sort of near at the bottom on the opposite side from what direction the welder was working. So that's a natural stress riser, a crack that could potentially be there. In seismic design, you definitely couldn't do that. For wind and low seismic design, it's just not recommended. It just doesn't seem like a good idea, just in general. So you recommend to go with the backing down there and just weld it as shown with the CJP. Or if you're in the shop with a small little cantilever sticking off the side of a column, say maybe you want to make one of those with a directly welded connection, then you could have fillet welds on both sides. You wouldn't have a fillet weld. You would not have a fillet weld only on one side of the flange, for the same reason. Now you have this natural crack in there, and that's just not a good idea.
All right. Moving on to slide 16. And we had a question about a term you used on this slide, but also used later in the presentation. Can you explain what you mean by overhead welding?
Well, looking at this slide, say you want to weld the bottom flange plate to the column, and you want to weld it in the field, and you want to make that bottom fillet weld. The welder will have to get under it and hold the stick up overhead to make that weld, and that's just not desirable. So we try to design our connections and the rest of the structure too, just any way we can to make it as easy as possible. And unless we really have to, we're not going to make them do the overhead weld. And there's just lots, as you can see, there's lots of other options as we talked about today. So we're going to avoid that. And in this case, we avoid it by primarily making that bottom flange plate. I mean, the non-obvious one is the bottom flange plate. I mean, the first thing that one might think if you started to design one of these is make the top and bottom flange plates the same width, narrower than the beam flange. But if you did that, you'd be forcing the guy to weld the bottom flange plate from below. So we definitely need that bottom flange plate to be wider than the beam flange. So we want to avoid that if we can.
All right. Going to slide 23. There was a question here. Should tensile rupture also be considered for the tension flange, treating the flange and half web as a WT?
I don't think one would need to do that. It's an interesting question, though. I've never seen that done in an example, and that thought hadn't occurred to me, to be honest. That's a cool question. I don't think so. I don't think one would really need to do that. Although you can always do it, right?
All right. Going to slide 36 and 37. Here you show this expression here for this limit state of shear transfer at the bolts. And so the question here was why, well, we had a couple questions. One question is why is this the sum of the minimum values of these limit states? Isn't it just the minimum of the limit states? And the other question was, can you clarify, is this the minimum at each bolt or the minimum overall for the connection?
Yeah, great questions. This is a somewhat newly explained limit state. There's a user note in section J 3.6 of the spec, and there's also a more elaborate user note in the 14th edition manual J 3.10. So you can read about it there a little bit. And the idea here is that at each individual bolt, say you're at one of the bolts, and at that bolt there's 5 things that can happen. You can have bolt shear rupture. You can have bearing of connected part number 1, tear out of connected part number 1, and bearing of connected part number 2, and tear out of connected part number 2. So you have 5 different failures that can happen at that bolt hole, associated with the hole and the bolt. At that bolt, you take the minimum of those 5, and that's the effective strength at that one bolt. Now you go to one of the other bolts and do the same thing there, and determine what the effective fastener strength is at that bolt. And you do that for all the bolts. So each bolt could theoretically have a different effective fastener strength. Gather all those up and add them up, and that would be your capital R sub n, shown in slide 37. Now that's in contrast to, I think it's called the poison bolt method. That's an older method where if you have an 8-bolt group, you could calculate the minimum of all of those for every bolt in the whole thing, the weakest bolt in the whole connection, and assign that weakest strength to all of the other bolts too. It's not the same thing as that. That's a very conservative approach. This new approach with the shear transfer is extremely rational. It makes perfect sense if you think about it.
All right. So let's go to slide 51. All right. And the question is, you're showing CU on both column flanges. When you check this, should CU be added, or should it just be checked for just CU?
Just CU. Just CU. It'd be just like if you had a column. Imagine you have a single-story column, and the load applied to the roof is 100 kips the reaction at the bottom is 100 kips. The axial load in the column is still 100 kips. It's not 200. It's exactly the same thing as that.
All right. Moving to slide 61. Let's see here. The question is, if the beams on the opposite sides of the column are different depths, such as the connection shown here, would you slope the stiffener plate if it was required?
I think there are different ways of doing that. I've never actually had that happen on a project, because I would on purpose make them the same on both sides if I needed to. But I've seen them sloped in detail, so I'm sure that can be done. So I guess if I needed to, I'd probably go that route. I mean, if the beams are a lot different depth, which doesn't seem likely actually, then maybe you'd have horizontal stiffeners you have three pairs of horizontal stiffeners maybe. Or you can have the sloping ones. It's just going to depend on the situation. So I guess the answer is, yeah, I might. Probably going to try to avoid it, though.
All right. We're a bit past time, but one final question. And the question was on this example problem. Do you need to check the CJP weld of the beam flange to the column flange, or is it assumed okay since it develops the flange?
Yeah, that's actually there's a big question there. I probably should have had some slides for this. But the one question comes about is, well, you're saying, okay, say you have the beam end moment is MU equals phi MP of the beam, and then you think, well, how can I develop MP of the beam with just welding the flange only? I lost all the web, right? I don't have any connection of the web there at the end. And that comes up sometimes, because if you calculate just the yielding strength of just that flange only, of course it's going to get killed compared to having the entire section at for phi MP, like with Fy times Z. So why can we do this? Well, the reason we can do this is because it has been shown you can develop MP of the beam with just these two CJP welds. And Larry Muir, I think it was Larry Muir and Bo Dowswell wrote a magazine article a couple years ago, maybe 2012 actually, that explained why. There's a couple of things here. One, the Fy and F sub U that we use are uniaxial values for coupon tests, and that's not the same as what we have here. These flanges have restraint from the weld to the beam flange has restraint due to the weld to the column flange. It has restraint in a big restraint transverse to the beam flange, just because of the weld to the column flange, and some restraint vertically as well. And the apparent yield stress Fy, if you had it for that case, is way higher than say 50 ksi. So there's that going on. There's I think there were some other effects there too. People talk about strain hardening there also. But I think that first effect is what's going on. So that's why we can CJP weld those. CJP weld is as strong as the flange, and the flange is good enough to develop MP because of those reasons. Again, it's a Larry Muir and Bo Dowswell, and I think that's a 2012 Modern Steel Construction article. Explains it very, very well.
All right. Well, thanks very much, Brad, for those answers. Unfortunately, we're